All right. Can you all hear me? Thank you. Okay. So, structural applications, of course. Bridge decks, they are using FRP in some demonstration projects. Wastewater treatment plant, that's a very good application to consider FRP bars. We'll talk about permanent formwork and other stuff in a minute. Now, repairs and rehabilitation, this is really going in a big way. For example, California has lots of bridges, very large bridges. Some of you may have gone to California. You'll see those bridge columns are 100 feet tall and 10, 15 feet in diameter. A lot of big columns. So recently they changed the earthquake resistance requirement. So they increased the capacity requirement for earthquake resistance. So by regulation, the state mandated or required every bridge column to be rehabilitated to resist larger earthquake loads. That may happen even in India because of recent data. They may change that requirement and ask you to improve the strength capacity of columns. In that case, you can actually use FRP materials, but it's a different form of material. I'll talk about it in a minute. And then there are pultruded members, and then in offshore platforms, they use FRP quite a lot. In fact, one of the Indian companies, they are fabricating lots and lots of these gratings. Everywhere you go, you'll see those FRP gratings produced in India. So you'll see them in a lot of places. So there are two types of two or even three types of FRP materials. One is internal reinforcement. I brought some samples. Be very careful. Don't touch these bars other than where I have covered them because they have very fine fiber, right? You know, it's very fine fiber. So it can poke you. And the sizing is, in this one it's silicone sizing. So it can give you a little bit of itch. So don't touch them anywhere other than where it is covered. So I have quite a few samples here, and Dr. Das also has some samples. So when you get a chance, you can come up here and take a look. So the first ones are FRP bars. Those are for internal reinforcement. Generally these bars are small diameter bars. This one is a 5 millimeter bar. 10 millimeter bars are very commonly used. Because of high strength, you can use smaller diameter bars. And then I have the traditional steel bars. You can actually hold these in two hands, one traditional steel bar and one FRP bar, and you can see the difference, okay? So I have pre-stressing tendon. Actually, this one here, this pre-stressing strand made from carbon fiber. So this was used in one of the bridges near my hometown, and they successfully used it in a bridge. That means it's not like theoretical product. It's a real product used in bridges. And many of you may have seen the steel strands, quite heavy. They're very good. And when you are jacking those strands, it's easier to jack steel strands. And I don't know how many of you are familiar with pre-stressed concrete. How many of you are familiar? So, okay, have you seen any plant, like pre-stressing plant? Have you seen how they actually tension? Very good. So they grab on this pre-stressing strand and they just start tensioning without any problem, right? You just hold it, that's it, no problem. They don't crush. Whereas this one here, carbon, is very soft in the other direction. So you grab on this, it will become completely crushed. So this is a Japanese design. So they designed a transition piece from carbon strand to regular strand. And then that transition piece actually is outside the beam element or the member. So they pull on this steel strand, and then once it is fully stretched, they anchor it, and that's it. And it worked very well. It's primarily in where I live, where Ohio State. Mostly we use pre-tension applications. That means it is tension first. The strands are tension first. You place the concrete, let the concrete set, and then you cut the ends of the strand. So that's pre-tension, right? It's not post-tension. So carbon strands may or may not be useful in post-tensioning, but in pre-tensioning for sure they can be used. So in my state, for some reason, we always use pre-tension because it has to be done in plant environment, and we have only a couple of plants, pre-stressing plants in this state. That's your pre-stressing. ACI 440 has one document just for pre-stressing strands and pre-stressing members, design of pre-stressing members. You can take a look, but it's really not, this is not as close to application as FRP bars. What I mean by that is there's a long way to go before you can use pre-stressing tendons made from carbon fiber or any other fiber. There's also external reinforcement. We won't talk much about this at all, not much. I'll just give you a brief introduction to this, but our focus will be just on this internal reinforcement. We need another 1 week for this type of external reinforcement. We're not going to do that because of the time constraint. So you can have permanent formwork. I'll show you some pictures of what it is. Permanent formwork, which is like, this is a small tube, but they make larger tubes, and that can go in, and then you place the concrete inside this. It becomes very good, member after you do that. Wrapping and plating. Wraps means sheets wrapped to columns. Near surface mounted bars. Design of NSM members is similar to internal reinforcement design, but I put it here because it's a surface application. Then pultruded sections, you have FRP pultruded section, these ones. It's just like steel members, okay? Just like steel members, everything exactly like steel members. And they use this in waste treatment plants. They are able to use this. It's not as strong as steel, not at all. Particularly in pultruded condition, they are not. So those are the three classes of applications. So let's talk about the internal reinforcement. So this is a bridge deck reinforcement. This mesh here is a bridge deck mesh. Unless I tell you that's FRP, you will not really know that it's FRP. It's completely similar to steel reinforced mesh. Then dowel bars. Are you familiar with dowel bars? Yes, very good. So dowel bars nowadays, they are very common. They use FRP dowel bars, which is common. The only problem with dowel bars is, we'll talk about it when I explain micromechanics. The strength in this direction, the dowel action, is very, very small because the fiber is in this direction, right? Longitudinal direction. Strength in the transverse direction is very, very poor. So that's a problem. But they are using FRP dowel bars. Internal reinforcement, they look exactly or similar to our steel reinforcing bars. I have just a few samples here. You can take a look. One of the major problems here is the deformations on the surface. Surface deformations is a big problem. These deformations are made with a spiral fiber wound spirally. Does it make sense? But that's not as strong as your steel ribs. Steel ribs are very, very strong, and the ribs engage the concrete surrounding the bars, and that's what gives you the bond strength or the pull-out string. Whereas in FRP, this can easily shear off at the surface. So these deformations can shear off at the surface. That's the major problem. So you need longer development lengths or longer embedment lengths. They're trying to copy the surface geometry of steel bars, but it is not as strong as steel ribs. So same thing here. This is a bridge deck. We have so this is a steel bridge with all these shear studs. You can see the shear studs, and then you have FRP reinforcement. So it's successfully used, and slightly more expensive material-wise, but it's possible to implement those in those applications. So here we have a beam column joint, which you can make with FRP bars. It looks something like this. We'll talk about the design of this kind of members. We really don't want to use FRP anywhere where there is compressive stress or compressive loads. So tunnel linings. This is a very common application these days, because look at this guy. It's an overhead application, right? And imagine using steel mesh here. They do use steel mesh, of course, but this one here is so light. So he's able to handle one person here, another person here. Two people are able to handle this mesh, which is a big advantage. Okay. And once it is in place, the mesh may look like this. It looks like this, just like steel bars. And tunnel lining is always subjected to a lot of moisture. There's always water seeping. If you have walked near the underpass here on campus, you see it's all wet, right? That water is coming from somewhere. So that's exactly what happens even in this tunnel lining here. So FRP is a good material. Of course, they do shotcreting, a lot of shotcreting for liners, but sometimes you need this kind of thick lining with a lot of reinforcement. And we have prefabricated ties and spirals. That's possible. We'll talk about some problems with ties later. And then pre-stressing cables, I showed you one of those. So these are all Japanese products. They are available to use. They will give you technology for even tensioning these strands. So they have a patented anchor system. I have no details. They do it themselves. So this can actually be tensioned. So precast, pre-stressed concrete bridges can be done with FRP. It's a huge beam. You can see how tall it is. These people are about 5'6", 5'10", 6 feet tall. So actually, I don't know if anybody knows Riscala. If you have done any research on FRP bars, you'll see Riscala name. This is that Sammy Riscala. He's a very eminent professor. Okay, now let's talk about external reinforcement. So here we have permanent formwork, wraps, near surface mounted bars, and so on. So what you see here is precast piles. So you have tubes, something like this. Here they are actually placing the tube first, then they'll place the concrete. But here they have tubes already filled with concrete. You pick them up just like normal steel piles, and then drive them. This is a pile driving equipment. You just drive the pile. So it's like just like any other steel pipe. You can do that quite easily. Or at least they have done it quite easily. So waterfront structures, you have these fender piles. Fender piles can be FRP tubes filled with concrete. That's what you have here. Same thing here. These are some naval facilities, so they have been using this for the oceanfront structures. You can have wraps for columns that will improve the strength of, or it will improve the compressive strength of columns. Generally speaking, circular columns will have better effectiveness in terms of strengthening. We are not going into design basics for external wraps, but generally speaking, I can just explain it to you without any slides. So this is another type. This is exactly what they are doing in California. So they are required to wrap all the bridge columns, I think by 2025 or something like that. I'm not sure, but it's mandated to rehabilitate all these bridge columns. So that's a big business in California. They are using it. And this is a robotic, it has a robotic arm, so it's wrapping and it goes all the way to the top. So what's the effect? How do we get the effectiveness from FRP wraps? This is what is done. Let's say this is a bridge column, and it completely crushed the concrete due to overloading in one of those earthquakes in Japan, I believe. So when the load is in the vertical direction, the column is overloaded and everything is crumbled, right? So if you see carefully, these bars are actually bowing out. You can see that, right? These bars, reinforcing bars, are bowing out. And unless you have very closely spaced spirals, this kind of failure is very common. So to prevent this, you put the wrap, it's like a sheet. There are some sheets here. I can show you there are some sheets here. We have sheets. So those sheets are wrapped with a polymer-based resin. So the polymer-based resin will actually impregnate, or it will completely soak the sheet. And when you wrap it, it's in place and it sets within very short time. So you don't have to hold it at all for hours. It just sets very quickly. And then when there is axial loading, there is a tendency of the column to expand laterally, right? You apply a load like this, you can see it here. The tendency is to expand laterally. So this fiber wrap is placed in the circumferential direction. That means it's holding it in a hoop direction. It's holding it. It's preventing that expansion. And this wrap has, or the material is very, very strong. It's fiber, so it's probably around 2000 MPa or something even more, right? The tensile strength of those wraps. So you put the fiber in the circumferential direction, that is radial in the other direction, hoop direction. That will prevent the lateral expansion. Because of that, you can increase the strength by a factor of 3, factor of 4. We can quite easily achieve very high strength. So we have done a lot of testing with basalt fiber. I have the fabric here. This fabric, not very strong fabric, but at the same time, with just 2 or 3 wraps, you can increase the strength by a factor of 3.5, easy. So if your original column can take 100 kilonewtons, let's say, after wrapping it will take 350 kilonewtons, which is tremendous increase. So that has a lot of potential even in India, I think. So if you are interested, you might want to pursue that kind of research and work. Okay, so this is in one of the big labs in California. They did full-scale tests, completely destroyed column here. It's completely crushed and failed. You apply the wrap, and then they do the testing again. Perfect. It retained all the strength and retained, and it actually gained more, like it's about 15-20% stronger than the column without any wraps. Okay. You can actually use these straps. We have some straps here. He says it is pre-stressing straps, but anyway, you can use those straps and glue them, or glue is a very non-technical term, but you put this adhesive and apply these straps just on the surface. That increases the strength significantly. It's a very common method to increase the strength of slabs. Okay. Of course, in this picture here, they are actually attaching fabric or wrap on a beam surface. So there are a lot of difficulties in applying this kind of wraps on surfaces. You have to do the surface preparation, and you have to design it carefully, and it is labor intense. You can see that. Anything involving labor will cost a lot of money. So that's something you want to keep in mind. And they are more skilled than the other workmen. So in one of the bridges in Manitoba in Canada, they actually did the strengthening of the web of a pre-stressed concrete beam. So that's also possible. Everything is possible. It costs money, but if you want to improve the strength, improve the performance, you can do that. So these are the external reinforcement applications. Okay, we won't talk about design methods for this. You can use, or you can get a copy of 440.2 R. This is 440.1 for internal reinforcement. They have similar report for external reinforcement. So you can get that, and you will see all the guidelines given in that report. Okay. So research, in my own lab, we have done a lot of this kind of strengthening trials. And for pre-stressed concrete beam, we had a 17 feet, about 5-6 meter beams, and then these are pre-stressed concrete beams. We completely loaded to failure. The top was completely crushed. So after the failure, we removed the top, added some grout to make up the geometry, and then wrapped it. And we were able to increase, not only recover the strength, but we also were able to increase the strength. So there are a lot of publications on strengthening of existing structures. You can take a look. And this is our protruded sections. I have some samples. Like I said, we have I-shaped sections. We have hollow sections, tubes of different sizes, because I just wanted to bring something light. I brought this small size, but you can get in large sizes as well. So there are lots and lots of these protruded sections available. There are no guidelines, no, I won't say that, but there are no American guidelines for design of protruded sections. There is a European guidebook which is using for using this kind of protruded section. Yes.
There is a thinking for protruded section. Can we use any steel codes or design?
No, that's the problem. Yes, that's the big problem. That's the reason, if you'll see, these manufacturers have their own data sheets. And if they are able to provide you data sheets, that will be great. But generally, they don't have them. Without going into too many details,